Welcome to the flock. Let's dive into this lesson and lab where we're going to collect hydrogen gas and then of course set it on fire because it's super flammable and awesome, and then do some calculations for that gas we've collected. Stick around to see how it's done. First things first, we need to know what the chemical reaction is before we can actually perform the lab or do any calculations for it. We're going to take magnesium ribbon, which we're going to symbolize by MgS for solid. We're going to add that to 6 molar hydrochloric acid, HCl. Now HCl is a solution, so we're going to represent that as aqueous. When those two things react, we end up with a single replacement reaction, where the magnesium is going to replace the hydrogen and become MgCl. Now since magnesium has a +2 charge and chlorine has a -1 charge, we do need to drop and swap and be mindful of our ionic charges here. So this 2 will go down there, and the 1 goes to the bottom of the magnesium, but we don't have to show that. That MgCl2 is going to remain in solution, so as aqueous, and then we have our product of interest, of course, the hydrogen gas. And now remember, hydrogen is a diatomic, so you're not just going to leave it as H by itself, you're going to have H2, and we're going to represent that as a G for gas or an upward arrow, since gases go up. If we balance this chemical equation, we notice there's 2 hydrogens here and only 1 on this side. So let's fix that and put a 2 in the front, and now we see that everything else is A-okay. Now that we know the chemical equation, we can do some calculations. The goal for this lab is to collect at least 100 milliliters of hydrogen gas. But how do we know how much magnesium and how much 6 molar hydrochloric acid to use to make 100 milliliters of hydrogen gas? Well, we're going to use our nifty-difty PV equals nRT gas law equation to help us out here. We know we want a volume of 100 milliliters. Now, of course, to use this in the gas law equation, the R gas law constant has volume in units of liters. So we need to convert this to liters. Move that back 3 decimal spaces because there are 1,000 milliliters in 1 liter. So we end up with 0.1 liter for our volume. What about this pressure? Where did I get this pressure value from? This 1025.4 HPa. Where did that come from? Well, if you go to your local willyweather.com and type in your specific city or the area you will be conducting this lab experiment in, you can find the pressure of your local area. My pressure here in Portsmouth today is the 1025.4 HPa. However, we need to think back again to this R constant. The R constant does not have HPa as its pressure unit. It has ATM if we happen to be using the 0.0821 unit. So we're going to need to convert that HPa value we got from Willyweather into ATM first.
Sounds like a job for the magical line to freedom!
If we know that 1 ATM is equivalent to 1013.25 HPAs, we can do a conversion from our HPA to ATM. Let's do this. Now that we have our pressure and our volume, and we know that the R value we'll be using is the 0.0821 with units of ATM times liter over mole times Kelvin, we also need to figure out what the temperature is, of course in Kelvin, so we can match our R units. The temperature inside this room where the lab will be conducted is currently 24.45 degrees Celsius. But that's not Kelvin, and we just said we needed Kelvin. So to convert it to Kelvin, we just add 273. And we end up with a glorious temperature of 297.45 Kelvin. That's what we're going to plug in up here. Great, now that I have all my variables to plug in, all that's left to do is solve for N so we can figure out how many moles of hydrogen gas could be created under these conditions. And now to get N by itself, we need to divide off the value from both sides. And we see that the moles we should be able to collect of hydrogen gas are 0.004144 moles of H2 gas. Well, that's great and all. Now we know how many moles would be in 100 milliliters of hydrogen gas under all of these pressures, but how do we figure out how much magnesium we need to mass out for the lab? How do we figure out how much HCl we need to measure out to react with all the magnesium in the lab?
Sounds like another job for the magical line to freedom!
Let's take the moles of hydrogen gas and convert that to grams of magnesium to figure out how much of this solid we should measure out. See if you can figure it out before I show you. Pause the video now. So we know we need at least 0.1007 grams of magnesium to mass out. But then how much HCl do we need to fully react with that much magnesium? Well, if we just convert our grams of magnesium to now the milliliters of HCl we need to use, using the molarity of 6 molar HCl, we can calculate for just that. Go ahead and pause the video now and see if you can figure it out. Ready? Let's check your math. Alright, so we know we need about 1.38 milliliters of HCl to fully react with 0.1007 grams of magnesium, in order to create 0.004144 moles of hydrogen gas, or 100 milliliters, which was the overall goal. Now that we know the exact amounts of reactants we need, let's jump to the lab area and see how this experiment is done. Full disclosure here, I don't have a scale that's good enough to measure 0.1 grams of magnesium, so I did have to mass out 0.2 grams of magnesium instead. We are still going to react it with 1.38 milliliters of HCl. So if you have a better scale to use, make sure you're actually using the values you calculated for. I just don't happen to have a good enough one for it. So in the lab experiment, when you see me mass out 0.2 grams of the magnesium, it's just because my scale sucks, and I couldn't get 0.1 grams of magnesium to actually read on the scale. For this lab, safety is of utmost importance, so make sure you're wearing your goggles, your gloves, and you have a fire extinguisher handy if you are going to light the hydrogen gas on fire at the end of the experiment. According to our calculations, I already massed out 0.2 grams of magnesium ribbon, chopped into tiny bits. We're going to take our 0.2 grams of magnesium ribbon and add it to our reaction vessel. The objective of this lab is to collect hydrogen gas, so we need a sealed system where we can choose where the hydrogen gas is going. That's where this little lid comes in handy. We're going to seal the reaction vessel and also put some plastic wrap around it quickly to hope that it doesn't escape from the sides, and then collect the hydrogen gas through the tube into a graduated cylinder that's inverted into a water bath. We're going to use water displacement to our advantage in order to trap the hydrogen gas inside our inverted graduated cylinder. So first things first, let's fill this guy up with water. Fill this all the way up to the tippy top, past the graduated cylinder mark. The next thing we have to do is seal the top and invert this guy into our water bath. There we go. The better the seal, the less air we get in the graduated cylinder, which is the goal, because we want to collect hydrogen gas, not the air around us. Ideally, you'd be working in a lab situation where you have a ring stand and a clamp where you can hold this straight up and down. Since I don't have that at my disposal, I'm going to do a jerry-rigged version and just lean it against the bottle. The next thing we need to know is, well, where is the actual meniscus starting in our graduated cylinder? You may have accidentally lost some water when you inverted it, so we're not assuming that we have 250 mils here. Remember, we filled the water up all the way, so we have more than 250 mils capability in this container. Let's get it eye level and make sure we know where the meniscus is to start. Here you can see there's a little tiny bubble at the top. Now, it's almost nothing, but we still want to account for it. I think we can easily say that that's at least a couple milliliters worth of air pocket in there. So let's say that we're not starting with 0, but we actually have maybe 3 milliliters of air pocket trapped in there. Next, we need to put the rubber tubing inside the graduated cylinder, so our gas that's created in the reaction vessel has somewhere to go where we can trap it underwater. So without lifting this out of the water, we're going to funnel our tubing into the graduated cylinder. Try and push it up as high as you can go. Make sure your tubing doesn't get pulled out of your graduated cylinder, otherwise you're going to lose your hydrogen gas product. The next thing we need for this reaction to occur is 6 molar hydrochloric acid. From our calculations, we saw that we needed a little over 1.3 milliliters of our 6 molar hydrochloric acid to react completely with the 0.2 grams of the magnesium ribbon. So in this very shoddily marked syringe, I have measured out approximately 1.5 milliliters of 6 molar hydrochloric acid. Getting it closer to the 1.38 milliliters we calculated for is very difficult in this kind of syringe, and I don't have better measuring equipment. If you have better measuring equipment, then make sure that you are measuring the exact amount. Now here's the tricky part. The second that this hydrochloric acid touches that magnesium ribbon, the reaction starts immediately. So if you're working with a lab partner, it's crucial that you are getting this in the reaction vessel and sealing it as quickly as possible so that all of your hydrogen gas will actually go through the tube and into your graduated cylinder and not wasted to the atmosphere or the room around you.
Let's collect some hydrogen gas.
I did see a little bit come out the side there, so I know we lost some product. We can see the water starting to decrease as the hydrogen gas is collected. So as the air gets pushed into the graduated cylinder or gets trapped in there, we can see the air bubbles actually coming up the tube. Then the water goes down. So the water is essentially trapping it inside this graduated cylinder. You can see that the reaction vessel looks like it's condensing, and it actually feels very hot. That's how we know that this reaction is exothermic. We're going to give the reaction vessel a little swirl to make sure that we have reacted all of the magnesium ribbon with our hydrochloric acid. I do still see some bubbles in there, so we're going to give it a little bit of time to react. We can still see some reaction taking place. The magnesium ribbon hasn't completely dissolved in the hydrochloric acid, so we know that there's probably more magnesium in there than just the 0.2 grams, but my scale is pretty crappy, so you know, it's what I got to work with. There's sources of error right there. You can see the hydrogen gas actually forming. So the next thing you need to do after the reaction has come to completion, as far as you can tell, once the bubbles have ceased, if the magnesium is completely dissolved, or anything like that that lets you know that this reaction is done, we're going to take our tubing out from the graduated cylinder and move the reaction vessel away, which is still warm, by the way. Again, another sign that this was an exothermic reaction. And notice that I'm keeping the graduated cylinder under the water. If I lift it above my water line, I'm going to lose all of my hydrogen gas that I worked so hard to get. So make sure you keep the top of the graduated cylinder underwater. Getting down at eye level will help you determine what the final volume of collected hydrogen gas was. This is where it gets a little tricky because we're reading this meniscus from the upside down inverted graduated cylinder. Just keep that in mind. We're gonna have to take our final reading minus the initial reading of the little air pocket that was in the top here. So we overshot our collection of gas by, looks to me, maybe another 20 milliliters, maybe another 15 milliliters. Let's say 15. Not quite 20. So reading from the bottom of this meniscus, you can see that it's past the 250 line, inverted. So we're going to assume that we collected another 15 on top of that, so 265. Now, of course, the best part of this reaction is lighting the hydrogen gas on fire. But in order to do so, I'm gonna need an extra pair of hands. So I've called over my very handsome hubby to help me lift this graduated cylinder out of the water without losing any of the hydrogen gas in order to light it on fire. Please welcome to the stage my wonderful, handsome, amazing husband, Jesse. So in order to do this, he's going to put his hand under the water and create a nice tight seal on the palm of his hand and the opening of the graduated cylinder. You're probably gonna get the table wet when you try this, that's okay. Then, once he's got a nice tight seal so that none of the hydrogen gas escapes, he's going to lift it straight up out of the container and invert it, keeping that pressure on the top so none of the gas escapes. And then, last but not least, working with your partner, you're going to light this on fire. 1, 2, 3. Ta-da! Thank you, lovely assistant. Luckily, we didn't have to use our fire extinguisher for this lab. Now let's head back into the classroom and do the calculations for all of the experimental values that we collected. Whoa, so we collected hydrogen gas and lit it on fire. Now let's do some calculations for that gas. We know that the mass of the magnesium we started with was 0.2 grams. Again, because my scale sucks and we couldn't measure out the actual 0.1007 grams that we should have measured out. Womp womp. The volume of 6 molar HCl we used was also closer to 1.5 milliliters in my very crappily labeled syringe, as opposed to the 1.38 milliliters of HCl we should have measured out. Again, womp womp. And the volume of the H2 gas we collected was our final volume of 265 approximated milliliters of gas, minus what we initially had in the top, that little bubble, which was about 3 or 4 milliliters. We're super guesstimating here, so let's say it was about 3 milliliters that we started with. So we would have collected about 262 milliliters of H2 gas overall. So in order to figure out our percent yields and our percent errors and all that jazz, we need to figure out the moles and grams of the hydrogen gas we calculated. We know that we had 0.262 liters of hydrogen gas collected. So let's convert that value into moles. Of course, we're going to need to use our PV equals nRT equation again in order to also account for the pressure and the temperature of the room that this lab was conducted in. The pressure is still the 1.012 ATMs that we calculated from before using the willyweather.com and our conversion factor for the HPA, and our temperature is also still the same in this room, which was the 297.45 K. So all we have to do is plug and chug using our new volume to solve for moles. So in our lab, we collected 0.01085 moles of hydrogen gas. So again, in order to figure out what our percent yield is from our actual versus our theoretical, we need our hydrogen gas to be in grams. So let's take those moles we just found and convert it to grams of hydrogen gas.
Here comes the magical line to freedom!
Don't forget that hydrogen is diatomic, so to find its molar mass, you need to multiply 1.008 by 2. So we see that the mass of our collected experimental gas came out to be 0.02187 grams of hydrogen. So now we can actually calculate for the percent yield, our actual over theoretical. Well, we still need the theoretical yield, so we have to figure out which one was the limiting reactant. We had 1.5 milliliters of HCl that we used in this experiment, or we also had 0.2 grams of magnesium that we weighed out. So we need to figure out from both of those values which one is the limiting reactant. Go ahead and pause the video here and see if you can figure it out before I show you. All right, here we go. So between these two values, it looks like HCl is the limiting reactant because it creates less hydrogen gas than the magnesium strip would. So then theoretically, the maximum amount of hydrogen gas we could create would be 0.009072 grams of hydrogen gas according to our HCl. Now's the easy part. Now we can actually calculate for the percent yield, which was just actual over theoretical times 100. The actual amount we calculated for from the lab value was 0.02187 grams. That's how many grams of hydrogen gas we actually collected in the lab. But theoretically, we should have only been able to make a maximum of 0.009072 grams of H2 gas, according to our hydrochloric acid, which was the limiting reactant in this case. We're going to take that and multiply it by 100 to find a percent yield of 241.07%. So we created way more hydrogen gas than we should have, by 241.07%, so way over 100%. Huge amounts of error here. But this should give you something interesting to discuss in your lab report in the error analysis section. Okay, but what if the room that I conducted the experiment in actually decreased in temperature to 18 degrees Celsius? What would be the new amount of volume I could have collected of hydrogen gas? And how much impact would that have on my lab results? We can use Charles' law, which is just V1 over T1 equals V2 over T2 to see what kind of impact this would have. Initially, we collected 262 milliliters at a temperature of 297.45 Kelvin. And we want to know what our new volume would be at 18 degrees Celsius, which we have to convert to Kelvin as well. Now if we solve for x and multiply both sides by 291 over 1, so at 18 degrees Celsius, if the room were to become colder, notice that the maximum amount we should be able to collect would be 256.32. That would be a difference of about 5.68 milliliters from what we actually collected in this lab. So the effect that that would have on our lab experiment would be that literally our volume would decrease of the gas we collected, thanks to the temperature in the room, which would also subsequently throw off the rest of our calculations. As in any lab, we want to wrap up the entire experiment in a summary. So according to the experiment that we conducted, we found that we actually gathered 262 milliliters of hydrogen gas when the goal was just 100. So we collected 162 milliliters more than we anticipated. We were also able to use PV equals nRT to figure out how much of the reactants we should use to begin with anyways to try and collect the 100 milliliters of gas, and then use the PV equals nRT equation to also calculate how many moles were in our experimentally collected gas. From there, we were able to do some dimensional analysis magical line to freedom calculations to determine the limiting reactant between the reactants we used experimentally and figure out how much grams of hydrogen gas we collected versus how much could have theoretically been made to solve for the percent yield of this experiment, which we found to be loaded with error at 241.07%. Yikes. And then we also saw how decreasing the temperature in the room after we collected the gas in the cylinder would have also skewed our data because it would have showed up as about 5.6 milliliters less. Hopefully you now understand how to collect a gas experimentally and then also use the gas law equations to do some experimental calculations thereon. Please give this video a quacks up, and when you're out of luck in chemistry, subscribe to the Duck.
No ducks, no glory.